Santosh Vempala to tell us about M-Ellipsoids.
So the title of my talk is Deterministic Algorithms via M-Ellipsoids. And it's a joint work with Daniel Dadouche, who's a student at Georgia Tech. He's, in fact, he's graduating this spring. And, but before we get to the new work, there's a lot of nice motivation and background, and I'd like to cover some of that. Till about 2 years ago, I didn't know what an M-ellipsoid was, even though I was using ellipsoids quite a bit, and as I guess all of you know, they're very useful in computer science and algorithms. So starting with the ellipsoid algorithm, where convex minimization is done by a sequence of approximating ellipsoids. And in fact, all known polynomial time algorithms for convex optimization use some sequence of affine transformations which are equivalent to finding ellipsoids. For a different fundamental problem, for sampling convex bodies, also ellipsoids are very important. Indeed, using the reason is that you want to sample some body, and if it's very long or very in one or more dimensions, it might be hard to get under control, even to go from one end to the other end. So it's nice to be able to apply a transformation that first makes it round. And so the classical John theorem already gives us some approximation, and I'll put it up just to introduce a bit of notation or to remind you. So the John ellipsoid gives us for every convex body K in n-dimensional space, there is an ellipsoid which sandwiches it to within a factor of n. And it will be convenient to call this minimum sandwiching ratio, this is the Banach-Mazur distance, or the usual notation, K with a ball in n dimensions, Euclidean ball. So by this we just mean the minimum sandwiching ratio you can achieve by any affine transformation of this. Okay. So this is at most n for any convex body, and it's tight for a simplex. Now in terms of algorithms, finding this is hard. However, using a variant of the ellipsoid algorithm, Lattice gave a method soon after the ellipsoid algorithm where you're able to find an ellipsoid E which achieves a slightly worse sandwiching ratio of, so algorithmically, and by this I mean in polynomial time, you can find E such that this is sandwiched between n and a little bit higher. That's what you can do. Yes, but the remark is already in an earlier note, right? Numbers, graphs, and convexity. This,
yeah, but it's in an earlier paper.
Okay, okay. With that's not the folklore, but I believe you. So it's with Grochel and Scriver, and that's still the best known, this root n approximation, and an interesting problem to see if you can prove a matching lower bound. Now in fact one can achieve a better sandwiching ratio if instead of using the John ellipsoid we use the inertial ellipsoid, and this is just the ellipsoid corresponding to the covariance matrix of a random point from the convex body. And so So it's just the ellipsoid of all points x, where say A inverse x minus z has length at most 1 is the 2 norm, and here z is the expectation of a random point from the convex body, and A squared is the covariance matrix. So this one has the property that in fact you get a sandwich the bound of n also. It's a different ellipsoid. In general they're very different, but you get the same sandwiching bound. So let me just write down precisely what it is. You get that if you take this ellipsoid, you have that it's slight scaling of it fits inside the convex body, and then a factor n scaling of that contains it. So again, the sandwiching ratio, even for this ellipsoid, even for this transformation, is n. Now the advantage of this is that you can find this to arbitrary approximation in polynomial time.
So
Why
why isn't this better result, strictly better result? I mean,
So-
no reason to particularly prefer the German.
It's randomized. So one reason is that the only way we know how to compute the covariance matrix or the centroid is sampling, and yeah. Whereas this is completely deterministic.
But the initial ellipsoid can be different from the John ellipsoid.
They are very different. For the purpose of approximating, they can be very different. In fact,
Ellipsoid is required to have the maximum.
it's by definition it's just a max volume ellipsoid inside a convex body. Now, if you go to centrally symmetric bodies, then this ratio here is root n for the John ellipsoid, but it's still n for the initial ellipsoid. So, but in general, I mean, for this purpose, there's no reason other than randomness. Okay. So these are two things that are very, very, very useful. And so there is seems to be a third different and fundamental object called the M-Ellipsoid, and so in the course of this talk, I wanted to define what it is and why is it useful for algorithms. Okay, but I won't start with the definition. Let me start with some motivation from a different fundamental algorithmic problem. We've already seen convex optimization and sampling. Let me put up a different basic problem. And this is integer programming. Okay, so this is the problem where you're again given a convex body in n dimensions, and you want to find a point that's with all integer coordinates inside the body. So find x in k intersect z to the n. If it exists, otherwise declare that it's empty. Now this is I mean, as you can see, it's a very general great problem. You can, if you want, instead of z to the n, make it a general lattice L, and then you could say find x in k intersect L. It's useful to look at the general version sometimes.
But you could do a change of basis.
You could do a change of basis. From this perspective, it's not that it's the same. It's equivalent, yes. Now, the status of this problem is that I should mention that something I found out fairly recently is that the problem, and this as a general model for operations research, was proposed by Danzig early on. In fact, in his paper, there's a nice paragraph where he tries to say that tries to introduce that maybe this problem is complete in some sense, like you can reduce so many problems to this. And this was prior to Cook and Karp and much before, and also before Edmond's paper on polynomial time algorithms. So it had this hint. Of course, we know now know it's NP hard. And as far as algorithms are concerned, so after Danzig, I think this was 47, Lenstra in 83 gave a method that's polynomial for any fixed dimension, polynomial input for any fixed dimension. So the complexity is some function of n times polynomial in the rest of the input. So the function was 2 to the n cube, I think. Then. Yeah. But the point was a fixed n, you could do this polynomial input. And then in a dramatic improvement, Kannan in 87 made it n to the order n. And there's essentially been no improvement since then. There's been a small improvement. Now if you look at the exponent here, it's n to the 5 over 2n. And Hildebrand and Copy in 2010 made it n to the 2n. One of the consequences that I'll describe is that this approach, so these are all based on the same algorithm, Lensstra's idea for integer programming, which I'll describe shortly because it will motivate some of the talk. Using the same approach with Daniel and Chris Pikert, we could bring it down a little bit further, n to the 4/3 n, and it makes it simpler. And so one question that's I think quite nice here is, can we solve, is there a 2 to the order n algorithm for integer programming?
So I think if you had, okay, I mean, Ankura and I were talking about this the other day, so
Great.
I think we decided that if you could, then you'd get a better 3-set algorithm, 2 to the little of n algorithm.
So under the
Wait, I didn't agree to this.
You didn't agree to this? Okay. So let's
That would be great,
Let's
yeah.
talk about it after. So that,
If you get 2 to the order
or
n,
maybe
you
it was
don't.
if you get n to the
No, that was for
little-
the solving systems
Oh,
of
that's true.
polynomials.
So I think you don't think okay,
well, it sounds very interesting. So
yeah.
okay. So in fact, I was going to say a weaker version of this is there an n to the little o of n algorithm for integer programming? Okay. Okay. So
Oh, yeah, I take it back. Because we needed like quadratic rather than linear.
you'll have to explain later.
So
Okay.
all these algorithms are still polynomial in the rest of the input.
Yes. Yes. All of these are polynomial in the rest of it. That's right.
And randomized.
No, everything is deterministic till here. This, as published, is randomized, but in fact, as I'll describe, it's going to be deterministic. Yeah. Okay. Now, there's a special case of this, many interesting special cases, but one that we'll look at is the shortest vector problem. So now you again have the same setup. You have a convex body and a lattice, and now we assume that the convex body is either you assume it's centrally symmetric or just that it contains the origin. And the question is to find the minimum over vectors in the lattice, if you look at the length of the vector as defined by k. So this is just the norm defined by k. So that's just the minimum t where y belongs to tk. Right. So it's the I guess I should write in Milman, the smallest scaling of k that contains y. Okay, so normal Euclidean 2 norm, the k is the unit ball. Okay, so this problem, as most of you know, is very also has very nice applications, connections in computer science, and the motivation I want to put up is this theorem by Minkowski that says, so this quantity is usually called lambda 1 of KL, the shortest lattice vector, and we want to avoid the 0 vector, so it's other than 0, is that lambda 1 of KL is at most twice the volume of K, the determinant of L divided by the volume of K to the 1 over N.
This is for centrally symmetric.
Centrally symmetric K, yes. So this is with centrally. So let's just assume K is centrally symmetric for now, and I'll mention it when it's not. Thanks. So yeah. And so now what's the status of finding this? There is a polynomial time algorithm, LLL algorithm, Lenstra-Lovász, which lets you find a 2 to the n approximation, and some improvements to this. And then after that it's essentially wide open, because so let me just mention the status. There's if you just use Kannon's algorithm, you get n to the order n. And then there was a paper by AKS02. It's the same A as Aitai Komlo Simrati, but it's Aitai, but it's Kumar Sivakumar, and this is an algorithm that reduced that solved this problem for the case of the 2 norm in time 2 to the order n. So at least this special case is 2 to the order n. And then but this, I should mention, is it's a very nice algorithm. It's a randomized algorithm. It uses 2 to the order n space, 2 to the order n time, and 2 to the order n bits of randomness. So it's very heavily randomized, and it's Monte Carlo, so it has error on both sides. And then in 2010, Michiancho and Vulgaris came up with an algorithm for the 2 norm, which is deterministic and solves it in time 2 to the order n. Okay, so whereas Kannon's algorithm works for any k, these are for the 2 norm. Okay, so one question you can ask here is, can we solve the shortest vector problem, find lambda 1 exactly in time 2 to the order n for arbitrary k, and deterministically? So question 2, deterministic 2 to the order n algorithm for lambda 1 KL. Now I should mention just that since I put up this theorem, it's open to find, let's say, a polynomial, so certainly it's open to find a polynomial time polynomial approximation to lambda 1, but also a polynomial time polynomial approximation to this bound. And there is a result that if you can get poly n times Minkowski's bound, this implies poly n, a different poly n times lambda 1. And this was I read it in Lattice's book, but I think it's only by you. So yeah. Okay, and unlike in terms of hardness, I mean, I don't know why we know so little about this problem, just in terms of reductions also. But even what we know, for example, is that to the problem of deciding a factor n, approximately finding this number to within a factor of n, or actually root n, is an NP intersect co-NP. So it's unlikely to be NP hard, unlikely to have any kind of hardness that we know about, and yet the best known approximation polytime is exponential. Okay, so I'm asking a weak question here, deterministic 2 to the order n algorithm for lambda 1, even though there's no hardness. Yeah. Now the reason I brought this up is 2 things. First, we'll be able to say something about this. This question we can answer completely, but also because SVP is actually the core tool in. So you might ask, why do you want to solve SVP for general k? Why? I mean, B2 is the natural one, and that will give you some approximation, because you can always sandwich a body with an n, so you'll get some approximation. So why bother with general k? And so one motivation is this algorithm, which, in case you've forgotten or not seen, just remind you about. The Lenstra-Kannon approach. So how does that work? Also because it's the only method we have that's giving these bounds, so maybe there's a completely different algorithm. Yes?
So just make sure I understand. So say that K is the ball,
Mhm.
right? And you're looking at an arbitrary lattice. Isn't this this lambda 1 is like the shortest vector?
Yes, exactly.
Vector in the
Yeah, SVP, shortest vector problem, right, exactly.
Oh, okay.
Sorry, I should have said that more. Yeah, it's the shortest non-zero vector problem.
Okay, but then if K is
Some arbitrary,
thing, then so it's a generalization of shortest.
exactly, yes,
Okay.
right.
Maybe you did say it, but I wasn't.
No, that's what it is. So, I mean, it's interesting as a generalization, but it has a very specific motivation coming from the current approach to integer programming.
Okay.
So it doesn't seem to be so well known, so I thought I'd describe it, since there's been basically no progress on this method.
Can you remind us for AKS, is it really only for B2?
No, it's been extended now, yes. And in fact, AKS will work for, in this bound, yes, I should mention that. This was, in O2 they only did for B2n, but in fact it can work for any K using the same amount, 2 to the order n space, time, and randomness.
I think even in their original paper they started with B infinity.
Oh, is it? Okay.
It's one version.
I mean, there's certainly several follow-up papers which did it for, so this Arvind and Joglik are,
Oh, I didn't know.
yeah, they explicitly did it for SVP, and that was only last 2 years ago, I guess.
By
Yeah.
looking at like balls of different kinds, you can like get shortest vector under different norms?
Yeah,
This
so
model?
that's right.
So like if K is like the
Exactly.
points whose P's powers are something.
Right. So the LP balls was the special case of this, right?
Yeah.
Right. So that's right. They did it for LP balls, not just P2N, in the AKS paper. Yeah, but not for general K.
Also, this reduction between Minkowski and lambda 1, does it require you to be able to solve it for every K for the reduction to happen, or does it work K by K?
So there, it's sufficient to do it for just B2N. Yeah.
Also, for the Minkowski one for B2, will give you
Yeah, that's right. Yeah. Okay, so now the way the integer programming algorithm works is the following. So you have some convex body, and you want to check if it has an integer point and find one if there is one. So that's the form. So find x and k intersect Zn. And so we have to define two objects, the duals of k and of L. So the dual of k is a set of all y, so that for every x of the polar in k, the inner product, I'll write it like this, is at most 1. And the dual of L, the dual lattice, is the set of all x in the original lattice. So it's a smaller set where the inner product is an integer. So these are the objects. And so the approach is the following. We'll find a direction, 0 might not be in the body, we'll find a direction so that y star, say, so that if you look at hyperplanes orthogonal to this direction.
I'm sorry, but these are not the standard definitions of the duals.
Yeah, the polar, I guess I meant.
No, I mean usually it's over the whole space.
Uh,
In both cases, I would say. Certainly in K, I mean, you want it to scale oppositely to K or something.
so for
You cannot. It's not why. Sorry.
Absolute value missing this.
say again,
Yeah, absolute value missing the first definition.
Oh, but
Yeah.
K is
centrally symmetric.
Oh, okay, sorry, yeah, okay, yeah, I take it back, it's fine.
It's okay. Yeah, comes to the same.
Fine.
Okay, so we'd like to find a direction so that if you want this direction to be so that the integer points only live on a small number of hyperplanes that are all orthogonal to this direction. Okay, so in particular, we'll only pick y star from L star. So the approach is find y star in L star minus 0, and then you look at hyperplanes that are all orthogonal to this, h1 through hk. so that, well, first there's going to be some easy cases. If either the body is too big, it contains a large ball, or too small, you'll either decide, look, there's no integer point, or there's easy to find one, and you're done. Otherwise, you want to reduce the dimension, and for that you find these hyperplanes, and then reduce the problem to trying to find an integer point in the union of k intersect the lattice intersect each of these HIs. So in other words, you're going to recurse on k intersect HI and L intersect HI. So now if you could put some bound on the number of these planes, so suppose we could put a bound of f of n on the number of these parallel planes, then the complexity of the algorithm would be about f of n to the n, because you get n blow up and then n minus 1 and so on. Let's say f of n is an increasing function of n. So okay, so how do we find this direction that gives you a small integer width, we call it. So this is going to be just an SVP problem. So I'll write it down because I find this useful. You want to find the minimum over all y in the dual lattice of the supremum, so the largest and the smallest integer point. So supremum of x, y, where x is in k, minus the supremum x is in minus k, which I can write as infimum of x, y, x in k. Right, so that's the same as I'll combine that as the supremum over the difference body k minus k. It's all things that you can get as x minus y, and then this is just xy. And this is just the dual, the norm under the dual of the norm of y under k minus k star. You expand the definition of the dual norm, and now this is just the SVP problem. Lambda 1 k minus k star is the body defining the norm, and L star is the lattice. Okay. So now the way that it's actually done in these algorithms is because there was no method for doing this. Well, let's just approximate this with balls, sandwich between balls, and then apply say LLL, the 2 to the order n, we get an approximation and use that to continue. So you'll pick up factors of n to the constant times n, but that was not a big deal for n to the order n out. But if you want to go below, we better take care of this. So at least if we were to find such an algorithm, this would be in the required time. The last thing I want to mention here is what bound do we get on f of n if we manage to do this. So there's a nice simple bound that says that the covering radius of the lattice using the copies of this convex body times this lambda 1, this exact lambda 1, k minus k star with L star is bounded by, this bound is called the flatness of this pair, and the current best bound on f of n is n to the 4/3 for general bodies by Rudelson. An earlier n squared bound was in a paper by Lovas and Kannan, and it's possible that you can improve it to n log n. Okay, so this is the smallest scaling of k, so that if you add it at every point of the lattice, you get all of Rn. It'll take a few steps to show that bound, but so that gives an upper bound on the number of planes. Now, unfortunately, so this will, once I give you a method to solve this using this bound, we get n to the 4/3 n as claimed here. The best we could hope to do this is reduce it to about n, but you can't go below that. So this approach somehow hits a wall here at n. Last thing I want to say about integer programming before I switch to giving algorithms.
Aren't there much better bounds known when k is centrally symmetric for the flatness?
Yes.
When or something?
K is not, right? We're not assuming K is centrally symmetric.
Oh, yeah, but I'm saying in that case.
In that case, you do get better bounds. It's correct. Yes, when k is centrally symmetric, you do get better bounds. Of course, when k is centrally symmetric, integer programming is trivial. But
okay.
zeroism.
Oh, yeah, sure.
But you're right. On the other hand, there is a paper by Lovas and Kannan where they give a possible approach, generalization of this, that has the potential of log n to the n. And the idea is, instead of going down, finding these one-dimensional directions which are sparse, how about maybe there is a subspace of some dimension, so that if you look at what sparsity it induces, it's log n to the corresponding dimension. So rather than n, and when you're going down to one dimension, you're projecting orthogonal to one dimension, project orthogonal to some k dimensional space, and you pick up not n to the k but only log n to the k. And this is untested, open. The best lower bound for this approach is log n. Okay, so this so much for motivation and the connections. So now I want to switch to algorithms and trying to answer these questions and how the M-Ellipsoid shows up playing a prominent role. So there was I mentioned this result by Miciancio and Vulgaris in 2010, where they solved lambda 1 B2n for any lattice in time in deterministic 2 to the order n time. It's a very nice algorithm. So what they do is they define a graph on the lattice, whose vertices are the lattice points, and then the edges, they connect two lattice points if the difference corresponds to a Voronoi relevant vector of the lattice. So look at the lattice and define the Voronoi cell, all the points closest to it, which is a copy of it everywhere, and then you have normal vectors to these facets. Those are the Voronoi relevant vectors, and the key insight there is that that's not too many. There are only about 2 to the order n Voronoi relevant vectors, and therefore you can actually traverse this graph. They should describe how to traverse this graph. So you're able to find a scaling of the ball where you have at least one point, and then just traverse this graph till you find one in, or decide that there's nothing in there. So it's quite nice. And one way to state that theorem is that for any ellipsoid E, the set E intersect L can be enumerated in time 1 plus the size of E intersect L times 2 to the order n. So it's E is any ellipsoid. So once you can do it for a ball, you can do it for any ellipsoid, and I'll just state it here for convenience as an ellipsoid. So you have some ellipsoid and you want to enumerate all the lattice points inside that for some lattice. You can do this in time that is just the number of points times 2 to the order n. So it's the same algorithm. You can view it like this. Okay. Now, so it's natural to say, why not try this approach for general K, say cubes or even other LP balls. But it breaks down in many places, including the size of the Voronoi relevant set. And it's not clear how to improve on n to the n.
It would seem like you could take your convex body, inscribe it in an ellipsoid, and enumerate the intersection with the lattice and throw out the points that don't.
Right. The trouble is that when you do that approximation, the size of the intersection can go from potentially 1 to n to the n.
Okay.
So the ellipsoidal approximation could have many more lattice points.
So is this Voronoi relevant set somehow related to Scarf's neighbors, or?
It seems a bit different. Yeah. It's not the formula. Yeah.
The Voronoi cells have just exponentially many facets.
Exactly. 2 to the order n.
And that's true for every.
Only for this. For every lattice for the Euclidean norm. I mean any ellipsoidal norm. Yeah, that's right. And so even if you go to sort of a cube, it seems to be n to the n. That's one problem. But there's more to that.
Are there lower bounds known for?
I believe for there are now some convex bodies for which you can actually show the number of relevant vectors is large. Now, unfortunately, that's not the only issue you hit. The way they build this, they have to do this recursively, and it's nice for them that when you go down to a lower dimensional space, the Euclidean norm remains the Euclidean norm. Ellipsoids remain ellipsoids, which is completely not true for other LP balls. So there are several difficulties. That
I
seems
see,
fun.
and even the worry would be the intersections of different, layers might even be different.
Completely, yes, exactly. You might get different convex bodies, so you'd have to do it for general convex bodies potentially. and then yeah, even the Voronoi cell is not convex. Here at least it's a polytope. So, yeah. Okay, so what should we do here? So here's the result that we had with Daniel, Chris Pikert in 2011. And what it says, for this, to define this, I have to define one more thing, which is, let me call GKL the maximum. So this is just like the number of points in K intersect L, except for any shift of K. So it's the supremum over X of the size of X plus K intersected with L. So I'm allowed to shift K now and see what's the maximum number of points you can get in K. Okay, so the theorem was that given an M-ellipsoid of K, which I have not defined, but just think of it as some ellipsoid, so it can be given explicitly as a matrix. K intersect L can be enumerated in time the size of GKL times 2 to the order n. Okay. So two things here. First, we need an M-ellipsoid, and second, we're picking up not K intersect L but GKL, which could be different. A shift might have many more points than the original. Okay, but once you have this, you actually get the results we want for, say, for SVP and IP. So corollary, given M-ellipsoid of K, lambda 1 KL can be solved in 2 to the order n time for any K now. Given M-ellipsoid, yes, everything is deterministic. So I'll mention. I'll say it in a second. Okay, I'll prove this. Yeah, but yes, it's deterministic. So, but given the M-ellipsoid explicitly, so that part still, yeah. And as a corollary of this, or IP can be solved in n to the 4/3 end. Okay. So let me just prove why this corollary follows from this. And so what do we really have to do? We have to bound GKL, right? So to find lambda over KL,
Did you define the M-ellipsoid?
I have not defined it.
Oh, you have. Okay.
I haven't defined it. But you see, this one also I haven't defined it. So, right? So this is using. So it's okay, right? Yeah. I want to make sure by the time I define it, you can't wait another minute to hear what it is, especially if you haven't. Okay, so right. So well, how would you do this? Well, we have to guess a scaling of K where we get at least 1 point. Now, if you could guess it so that there is 1 point, it's still problematic, right? Because GKL could be very large. That's the concern. But ideally, what you do is you'd guess a scaling of K where you get 1 point and not too many points, and then run an enumeration in there. Because this is letting you enumerate K intersect L. Okay, so let's say we guess, suppose we guess at T so that lambda 1 is less than T and at least T over 2. Okay, so this I'll do by starting with a very small bound, like what you would get from the ball contained inside K, and then, the ball containing K, and then double it till you get at least 1 point. Of course, it's still not clear that when you hit 1 point, you might hit n to the n points. So that's the only thing I need to prove, that when you do hit 1 point, you hit only 2 to the order n points. Okay, so why is that true? So in fact, for this value of T, it will be the case that GTKL is at most say 5 to the n. So when you hit the radius where lambda 1 is above but less than T, then it will be only constant to the n. Once I prove that, we're done. Right? Okay, so why is this true? So now I have to bound this for every shift of Tk. So now the point is that because t over 2 is a lower bound, if I take some shift of tk, x plus tk, and any two lattice points of L, of course their minimum distance is lambda 1. So I can put copies of k of t over 2k around each one. Okay, so I mean lambda 1 over 2. So y for any two lattice points y and z, y plus lambda 1 over 2k and z plus lambda 1 over 2k are disjoint. This is so in particular y plus tk over 4, this copy you can put around every lattice point a copy of tk over 4, and these copies are disjoint. Now the union of these copies is contained inside tk plus tk over 4. So I'll use this for so if I take each of these copies, all I'm saying is that the union of y plus tk over 4 for all y in the lattice intersected with k is contained in t has been shifted, so it's x plus tk over 4, okay, because that's the maximum you're adding, and therefore the maximum size you could have of lattice points is at most the total volume divided by the volume of each one, just a packing argument. So this is 5tk over 4 divided by, so volume of 5tk over 4 divided by volume of tk over 4, which is 5 to the n. Right? So we built a packing, disjoint sets, each one has volume at least tk over 4, and they're contained inside a slight blow up of k. So at least for the shortest vector problem, if you can, GKL is not an issue. It's as if you're enumerating k intersect L, but you still need this M-ellipsoid. Okay. So now let me describe so here's what I'm going to prove now. Now this is the proof of the enumeration theorem here, that given an M-ellipsoid, this is the time to enumerate it. I still haven't defined what M-ellipsoid is, but this so it's some ellipsoid. Okay, and what do I want to do? I want to enumerate everything in k, or all the lattice points inside k. So what we'll do is we have some ellipsoid. We'll cover this body with translates of this ellipsoid. So cover k with translates of E. There's k, and this is the given M-ellipsoid E or some ellipsoid E. You're going to cover k with translates of E. So it'll be something, but this is a covering. Okay, and then enumerate E intersect L for each translate, for each copy. Now when you do this enumeration for each point, check if it's in k, and if it's in k, put it on your output it, otherwise no. So this is the algorithm. What's the complexity of this algorithm? So the complexity is, so let's define nke to be the covering number of copies of E required to cover k. So you have to cover k with E, so that's the number of ellipsoids, and then it's the number of maximum number of lattice points that could be in E. Now that could potentially be high, but how should we bound that? How should we bound the number of lattice points that are in E?
Well, the maximum number is GEL, right?
Yeah. Well, no. This is now we're asking for the number of lattice points in E,
Right.
not in K.
Yes, they said GEL.
GEL, yes. So what is GEL? We need to get the bound in terms of GKL. There is no E really, right?
Okay. I'm saying the bound you have is GEL, so you have to relate.
Right. I have to relate the two exactly. Yeah, the bound I would get a G. So, but however, imagine that we now cover E with copies of K. Okay, and then I can use the bound GKL. So each ellipsoid will now cover with copies of K. If I draw this, it will look trivial because the K is so much bigger than E. But in principle, to cover E, you need copies of K. To cover K, you need many copies of E. So it's N EK times GKL. Right? So this is a bound on the number of lattice points inside any one ellipsoid. Just because you're covering with K, and then for K we have a bound. Okay. So, say again?
That times 2 to the O of n.
No.
You're going to use the MV algorithm for every ellipsoid?
Yeah, so far it's just the number bound on the number of lattice points. Right. We're good. So once we have ellipsoids, the Micciancio-Vulgaris algorithm says there's an additional 2 to the over for the time complexity 2 to the order n overhead for actually enumerating this. So that's just a multiplication. So now, which ellipsoid would you choose? One that minimizes this. Choose E to minimize this product. So Milman's theorem says that for any centrally symmetric K, but in fact it works for any K, there exists an E such that this product is bounded by 2 to the order n. Okay. This is a, I mean, it's not just a matter of proving it, but you might not expect this. If you try to use the John ellipsoid, you would get n to the n as a bound for some bodies. So the fact that it exists is not, I don't think it's obvious. Yes, in fact, it's not in the original thing, but we can make it constructive. Yes, exactly. Yes. And,
You also need the covering, right?
sorry? How to construct the covering given the ellipsoid? So that's not hard. What we can do is replace the ellipsoid with just a maximum volume parallelepiped that fits in there, for example, and use that basis to cover the body just by an axis enumeration. So you can do a traversal of the lattice induced by those parallelepipeds. And these volumes are within 2 to the n, so it doesn't really matter whether you use ellipsoids or parallelepipeds. Right, so to construct the covering, we start with some ellipsoid and run this. Okay, now that's the enumeration algorithm. So now the question is how do we find this object, or one that gives us this bound? Now what's that? So this has a nice history in convex geometry, and it's still there's still nice new results coming up. It's turned out to be quite a powerful tool. We use it for all kinds of existence theorems. Milman. M is for Milman. Now, so as I said, the John ellipsoid, if you try to look at the covering numbers that it gives in general, it could be as high as n to the n. What about the inertial ellipsoid? I mean, these are all reasonable candidates for covering, right? You want to cover a K with ellipsoids, why not use one of these which approximates it? So inertial ellipsoid is a conjecture that root n times the inertial ellipsoid is an M-ellipsoid. So that seems like a simple thing if it would be true. Take the inertial ellipsoid, scale it up by root n, and that's already something that will cover with this bound.
This is the slicing conjecture, right?
But this is equivalent to the slicing conjecture. So it could be true, but we don't know how to prove it. On the other hand, using this perspective, there is a nice theorem by Klartag, which is essentially an alternative proof, very different from Milman's proof of the existence of M-ellipsoids. And what he does is, look, we don't know how to prove this. Instead, you can take your convex body K and generate a distribution So it's almost a convex body, but not quite. It's a log concave distribution. Log concave distribution, say pi, so that the inertial ellipsoid for this distribution is an M-ellipsoid for k. Okay. Inertial ellipsoid of pi suffices. And this gives a randomized polynomial time algorithm, and that's what we had back then using this. So the proof is essentially algorithmic. We just had to verify that each step can be done because you just have to generate this distribution using the polar of k and then sample from it to estimate the covariance matrix. But so it only uses polynomial in end randomness, because that's all you need to generate random points even from log concave distributions. And so it reduces the randomness in the AKS algorithm from 2 to the order n to poly n and makes it Las Vegas, so you can check that you.
Explain that theorem again?
So this is I didn't state the theorem because I'm not giving you the transformation here, but given a convex body K. As an oracle. Well, I mean, the way he stated it's just an existence theorem. For every convex body, there is a log concave distribution explicitly defined. So you have to pick directions from the polar of k, but each direction is weighted according to an exponential. So it's a log concave distribution from k, so that if you looked at that distribution and looked at its covariance matrix, the ellipsoid for that is an M-ellipsoid of k. What happens is that this distribution that he constructs actually satisfies slicing. So in fact, that's the way that a lot of geometers know his theorem, that for every convex body there is another one that's not too far away in a sense for which slicing is true. And
So it gives you a way to compute the M-ellipsoid of k?
Yeah, because all you need to do is estimate the inertial ellipsoid. Yeah, that's it. So if you could construct this distribution, which is just based on turning a membership oracle for k into a membership oracle for its dual. Again, that's in Grosjean-Loewe-Schreiber, and you then sample this log concave distribution, which we know how to do in polynomial time, and use that to estimate the covariance matrix. And so that works. So all of this we verified in.
What are you saying about de-randomization?
We'll get there. So this approach seems, I don't know, inherently difficult to de-randomize. Just as is, how would you estimate covariance matrix without randomness? Even if you were to just estimate the covariance matrix directly, it's not clear how to do it without some randomness. Okay. So there's a question here: can we make this deterministic? And so yes. So this gives a poly n randomness. Poly n algorithm for a M-ellipsoid.
Even the conjecture above would imply only a randomized algorithm.
That's right. Even the conjecture above would give a simpler method. I mean, but it would still be randomized. So this approach seems inherently randomized. Okay. So before I introduce the last part of this, which will be the how to make this deterministic, which is going to be based on Milman's original proof, and simplifications that have come since then due to Pizier. I want to give you one more motivation. At least now you know what an M-ellipsoid is. And so this is for another fundamental problem, which is estimating the volume. So given k, estimate volume of k. So this is the problem for which sampling is very useful, and you can get a polynomial in n randomized algorithm, as most of you know, Dyer-Friese and Cannon. And it's now, can we make this deterministic? And the answer is no. We knew that even before this algorithm came up, and this was work by Elekesh, improved by Barani and Furedi. And I want to state this
No, in the
in the oracle model. And indeed the main open problem I'll end with is what can we do about deterministic volume computation for polytopes. But before we get there, there's still some nice things. So they proved some quite strong lower bounds, and usually, at least so first of all, for the upper bound, you can get in polynomial time, you can get an n to the n approximation. Okay, by essentially fitting the body in a proper cuboid.
Can't you bound the number of random bits used by this algorithm?
It uses sampling. It's based on a random walk.
And it takes a lot of random bits to do that.
Poly n.
Well, it's not poly n. I mean,
You can make it linear. Go
you
ahead.
can make it linear by Nissan-Zuckerman.
Right.
But then you can enumerate those random bits.
Yeah, but it's good. It's actually going to be like n log n. You can't make it.
Yeah.
So that's n to the n.
N to the n.
It really
We already know how to do n to the n.
their result is the number of random bits is the space to describe a point in your
Mhm.
in your sample space, right?
Right.
So if you somehow reduce the number of points to the n, then the
Then
random
it's
result
potentially-
will use just a linear number of
Right.
bits.
Right.
So if you have an explicit description of the points in your space, those that you are enumerating,
Right.
then
This could be
a potentially de-randomization method. It will be a linear number of random bits, and you enumerate.
you at least get a 2 to the order n algorithm for
That's right.
this, right? So as it stands, this would give you an n to the n
Right.
approach, yeah. Right, which is already known with for volume anyway by a much simpler method. So you get n to the n approximation in poly time, and then what these results tell us is that if you were to only spend n to the a time, then the approximation factor must be at least there's a constant n to the a log n to the power n over 2. And in fact, if you look a little bit more closely, even if you wanted only a 2 to the order n approximation, you need 2 to the omega n time. And even more closely, if you wanted a 1 plus epsilon to the n approximation, you need 1 over epsilon to the 2n. And when I say time here, I'm sorry, I mean oracle calls. We're doing everything in the general oracle model. So this actually appears, Barani and Furedi actually wrote 2 papers describing these results in great detail, and given where we were, somehow this part got, at least I wasn't paying much attention to it, but it's open to achieve to match these bounds, to get 2 to the n approximation in 2 to the n time, or 1 over epsilon to the 2n approximation in 1 over epsilon to the 2n time, get a 1 plus epsilon to the n approximation using a deterministic algorithm. So now this is trivially solved if you have an M-ellipsoid, because an M-ellipsoid has covering numbers of c to the n. So if you're covering k with at most c to the n copies, and each of those can be covered by this, so the volume of k sandwiched and volume of E must be within factor c to the n. So just the M-ellipsoid's volume is already a 2 to the n approximation. And so finding an M-ellipsoid immediately implies this result. Now this takes more work. It doesn't directly give you this, but it turns out that if we take Milman's algorithm and run it at a finer scale, you can get you can solve this also. So you can get exactly matching bounds for this. Instead of 2n here, it's order n. So you can get one.
Which is Milman's algorithm?
I'll tell you that. I haven't told you that. So that's the last algorithm I'll describe. Okay. So you can get 1 plus epsilon to the approximation in 1 over epsilon to the order n time. So that's a result with Daniel that we just posted. Okay, so for the last 5 minutes. Okay. I'll just tell you what Milman's algorithm does, or Milman's method does, and sketch how we can make it algorithmic. So to define Milman's algorithm, a method, I have to give you a norm, define a norm, which is for any affine transformation A, the convex body K will define a norm on these matrices as the average length, the norm of these points under a Gaussian, the n-dimensional Gaussian, and make this to the power of half. So just so if A was the identity, so LKI, same, I'll also just call it LK, is the pick a random point from a Gaussian, standard Gaussian in n space, and look at its length squared. Okay, so this is LK. So gamma is the standard Gaussian. Now, what is this parameter related to? It will be very convenient to work with this because it's convex. And what we'll be able to do is write the first step of Milman's method as a convex program. Even though that wasn't necessary for his approach, he just needed existence. So, but to do this, what does LK have to do with approximating by ellipsoids? So if I define M to be the largest R, the largest radius for which a sphere of this radius intersected with K takes up at least half of the sphere intersects K. So you take the sphere in the same dimension, and you are going out to the point where half of the sphere is in K, at least half is in K, the largest place, so it's exactly half when this stops. Okay. Now the point is that these two are very closely connected, that LK is within constant times root n over m, and another constant times root n over m. This is not hard to see because when you're picking x from a random Gaussian, exactly, it's just concentration of Gaussian and of the volume distribution inside a convex body. Yeah, so you get these constants. Now the nice thing is that, or the reason why this is useful is that if you take the ellipsoid, which is just scaled by a factor that depends on LK, so the ball scaled up, then this gives a bound on the covering number. NKE times NEK for this scaled up ball is at most constant times LK star, the dual body, divided by n to the power of n. It's just a ball right now, but this bound could be arbitrarily high. I haven't put any bound on LK and LK star. So our goal will be to find an ellipsoid. Instead of minimizing the covering number, we'll minimize the product of these norms. Okay. That's the approach that they took to, that showed that there exists a transformation A so that LKA times LK star of A inverse is small. In fact, the exact bound is, so this is Pizier, and what he showed is that there exists an A such that,
wait, so on the right hand side you have this L star estimate,
yes,
right?
yes.
So I thought the best you can do there is like log n to the n.
No, it's I'm about to put that up. Yeah, so it's so there exists an A so that LKA times LK star, I'll just say A star, that's A inverse, is constant n and then log of the Banach-Mazur distance, the sandwiching ratio between K and B2n, which is at most log n, because we know this is at most n. So we're getting n log n here. There exists an A so that if you look at these numbers, it's at most n log n. Okay, and that's tight, you can't do better than this. So if you could minimize this product, you would at least get log n to the n bound. Now, so now this A can also be found, so lemma A that comes from the following convex program, minimize LKA subject to A semi-definite and determinant of A at least 1, achieves the same bound. Okay, in fact, that's how the proof goes, except they didn't worry about semi-definiteness, but we get that because LKA is rotationally symmetric. Okay, so this is staring at this optimization problem is what leads to this bound through a use of duality, which I won't do now, but if you could minimize this, you will get that bound. Okay, so now that takes us to two questions. First, how do you solve this convex program? I mean, these parts are easy. This is just explicit. I mean, we have separation oracles for all of this. The trouble is that the objective function is an integral in n space. So how do you even evaluate that? That's one question. Second question is, well, this is only going to give you log n to the n. You can't go below that. This program, actually, there are bodies for which it only achieves log n to the n. How do we get around these two things? So we had a SODA paper where we showed how to solve this and derive the log n to the n deterministic algorithm for all the results for which we had randomized. Okay, but now let's do the full thing. Last board that I use. And first step, how do we do the approximation? I mean, how to solve the program? Solving the SDP. Well, we can't hope to solve it as it is, so instead we'll define an approximation. So instead of LK, we'll have an L tilde K of A, which will be just the approximation that you get by replacing the Gaussian with the Bernoulli distribution. So we only evaluate it on -1, 1 to the n. So this is 1 over 2 to the n times summation of Ax to the k of k, where x is, and again a theorem of Bézier tells us that this approximation is not too far, that L tilde, the original Lk lies between L tilde k and is at most L tilde k times, again, a dependence on the Banach-Mazur distance, this time with a square root, although that doesn't really matter for our purpose. Okay. Now, okay, why does this help? Well, this preserves still convex. Let's go with the square, but it's still a convex function. Just some, because remember the x's are fixed, so it's a convex function of A. So now it's still a convex program, but now the evaluation takes only 2 to the n time. So it's a convex program where each oracle call where you're checking the objective value takes 2 to the n time, and then it's polynomial, say, by the ellipsoid method, as described in Grochel-Lava-Scriver. So this will give you the log n to the n. Okay. Now, finally, given this, how can we make this all n to the n? So what Milman described, and it's really an algorithm, it's an iteration. So he's going to start with this ellipsoid and improve it. So he's going to go through a sequence. So he's going to use this as the key subroutine and use a sequence of iterations. So the iteration.
So K is given as oracle access?
Oracle.
So,
K is oracle.
So how is this objective function actually encoded? I mean, so you
X is explicit.
Right.
A is explicit.
Right, but A is the variable, and you want to evaluate.
Right. So at a given
A
point,
of,
so it's like solving a membership test. You want to check for a given A, what's the objective value?
Okay.
Right.
Okay. All right. Yeah. Fair.
So this is all explicit. And okay. So so the iteration will go through a sequence of bodies. You start with the body K, and then you're going to construct K1, K2, and so on up to some KT. And the properties that it'll have is that if you look at the covering numbers nk K1 and nk1k, this product will be small, so that by the time you go to the end and you look at nk, I mean in general it's nki with ki plus 1 and then ki plus 1 with k, the kt will just be an ellipsoid, some ellipsoid. The products of these covering numbers will all be small. Okay. Now how can you possibly do that? Because we know that the bound we have on this is based on lk star, which could have a log Banach-Mazur distance bound on it, which in general is log n. So along with this process, the sequence of bodies here will have the property that the Banach-Mazur distance between ki and B2n is dropping fast. Okay. In fact, at the ith step, this will just be the ith iterated logarithm. So it will be the log, I'll just call it log to the I, that means log 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 I times of n, some constant. What we'll get in the algorithm is a cube because of the approximations you have to use. Okay, so it's going to, the sequence of bodies will, each one will look more and more like a ball and will maintain covering estimate so that the final product of all the covering bounds is still only 2 to the order n. Okay. So what is this algorithm? How do you construct ki from ki plus 1? Okay, I'll state that and stop there. Ki, sorry, excuse me. Yeah, so here's how we'll do it. First, given ki, we already have ki, compute this L ellipsoid, the optimal ellipsoid according to this convex program. I'll just call that an L ellipsoid of ki. So solve the convex program for the body ki. You'll get some transformation A. So the ellipsoid that you get gives you to get something that looks like some transformation of the unit ball. Now what we're going to do with this is two things. We're going to define an outer radius and an inner radius. So r in will be a scaling of this and r out will be another scaling of this. So root n, so it's just a scalar right now, log of I n L tilde k of a, let's call this ai in the ith step, and r out will be log in the numerator and then lk star ai star divided by root n. Okay, so these are two scalars I've defined. Once you see the algorithm, you can go back and derive exactly these scalars. So these are just to point out that these are explicit numbers, that's all. Okay, now the iteration is one line, so I should state that and then stop. So the iteration is the following. We're going to define ki plus 1 as the convex hull of take k, intersect it with the outer ball, r out times the ellipsoid corresponding to this, so ai b2n. So intersect with an r out scaling and take the convex hull of that with an rn scaling. That's it, that's ki plus 1. So I mean, the way you think about a convex body in high dimension is it looks like that. It doesn't look convex, but really if you think about a cube, that's what it looks like. All the corners have all this mass and in the middle it's small. And so what we want to make this round, so there is an outer ball or ellipsoid that cuts off all the very far spikes, and then there's an inner ball that might not be fully contained but takes out the regions that go very sharp inside. And then what you're doing is taking the convex hull of this ball with that intersection. Now given these definitions, the Banach-Mazur distance of the next step ki plus 1 is just going to be the ratio of these radii, is bounded by r out divided by r in. Now I won't do the full calculation, but the reason for this choice is to make this small. No, small, yeah, exactly. Yeah, so it's this for the covering number the product is small, and for the Banach-Mazur distance it's just dropping rapidly. So this is going to look like log to the I of n cubed. Yes, this bound here. That will be the bound. But that's the complete iteration. So we can implement every step of this, of course, and if we do this iteration more slowly, then you get the 1 plus epsilon approximation. So I'll stop here. I think the main, there are many questions, but maybe one that I don't know if any nice tools for is take the case when k is an explicit polytope. And for that, still the best known volume algorithms, the best known norm SVP algorithms are based on this general approach. And therefore, we don't know anything better than 2 to the n deterministically.
Did you define the M-ellipsoid?
Yes, it's the ellipsoid. It's any ellipsoid for which the nke times nek, the covering number, is bounded by c to the n.
Oh.
So it's sort of a looser definition than the other ones.
So it's just an ellipsoid.
It's any ellipsoid. Yeah, any ellipsoid that achieves these is called an M-ellipsoid. There are several equivalent definitions, but only up to constant to the n.
Maybe we're already into the questions. Yeah, more questions.
Maybe you can summarize again. So what's the main result? Can you say that again?
The main.
Deterministic.
Okay. So no, 2 to the n. It's everything 2 to the n. Now. Yeah, yeah. Everything deterministic. 2 to the order n algorithm for finding an M-ellipsoid. That's the basic thing. Deterministic 2 to the order algorithm for M-ellipsoid. Now this immediately gives the consequences for the SVP that I described and for CVP that I didn't go into because we just
over
any k,
norm, yeah.
any norm.
So it's just a de-randomization of the known randomized improvement of AKS.
Yes, so it's now you can think of this as a de-randomization of AKS, but it's completely de-randomized now for SVP anyway. Yeah.
So how come you don't lose anything from that approximation of AK?
This was the iteration. So if you were to do it just once and directly go to that ellipsoid, you get log n to the n. But we don't go so aggressively. Instead, we use the ellipsoid to get the next approximation and repeat this procedure. And at each step, the point is look at this approximation here. There's a log dBm here. So there is some hope that as your body is getting rounder and rounder, this is giving you a better and better approximation. So the more round your body, the better the approximation. There is actually some weak analogy with the way randomized volume algorithms go, where they're also rounding and sampling go together. And as you get more round, you get better samples, and so on, through a sequence of iterations. But maybe it's too early to say something very concrete about that.
But the quality of your ellipsoid is the product of all these NK.
Exactly. So if you look at that definition, which I haven't put down, if you look at the definition, each of these will be bounded by not by 2 to the order n, but by 2 to the order n divided by a factor which even when you add up over all of this still gives you only 2 to the order n. So the choice of these these log n over root n and root n over log n is just set up so that this product still says 2 to the order n, and that ratio, of course, this is a outer ball to inner ball is dropping fast. So if you look at the R out to R in ratio, it drops fast, and you don't pick up too much in the covering number. I mean, you don't expect the covering number to be large, right? So suppose you wanted to bound nki with ki plus 1, you just bound nki with this ball, with this k intersect, with only the outer body. And if you wanted to do the other side, ki plus 1 with ki, just use the inner one. So it gives a strong control on the covering numbers.
So what is the Milman ball for Milman ellipsoid for the L infinity ball?
It's just a ball, scaled ball.
Okay, so it's the same as John's ellipsoid.
A different scaling, but yes. John ellipsoid fits inside. Milman ellipsoid would be one of essentially the same volume.
Okay, so the hypercube is not an example where the covering number of the John's
No, it's not.
Okay, so what is an example?
If you take I think a double cone, you'll get an example where the John ellipsoid should give you only root n to the n covering number.
Okay.
And in fact, inertial times root n, which is of course still a conjecture, gives you an M ellipsoid.
All right, thanks a lot.
Thank you.